I'm Devin Sumrow.
And our topic is Industrial Wireless Communication System for Notification. So industrial settings require a continuous stream of data for its systems to work. However, abnormal noise, thick concrete walls, and machines are inhabiting pathways of data transmission. An RF system works in such environment because it communicates through various data packages. The first prototype of this project was developed by a previous ECE senior design team. They were able to make handheld devices which communicated and sent short messages between the devices. However, they couldn't communicate long enough for industrial settings. The goal of this project is to design a router which expands the star-based RF relays proposed. The solution we chose for this project was a custom printed circuit board. To further describe our solution to this need and the process that went about designing, creating, and then testing the devices, we will discuss the overview of the project, the required specifications, hardware aspects, software aspects, and validation and testing the design. For the functional requirements of the project, it has to have long-range communication. It has to be able to communicate in burst noise environment, which, as I said earlier, includes the thick concrete walls and the large metallic equipment. It also has to have error checking. As for the physical requirements, it has to be durable, it has to be compact, a compact system with a designed PCB board, which are more reliable and more compact. It also has to be compatible with standard equipment, such as screwdrivers. This graph here shows the system architecture. Our system consists of handheld devices and routers and transceivers. So when a handheld device wants to send a message to another handheld device, which isn't close enough or within its range, it sends the message through the routers. If the routers aren't within the range to send the messages between the handheld devices, the messages are sent through the transceivers. Jalika will now talk to you about the hardware aspects of the project.
So for our senior design, we designed this router. And I'll first go over the overview and explain the key components of this device before I explain how we actually did it. So in this device, we have a PCB board. And this PCB board has three primary circuits: the microcontroller that has a JTAG and goes JTAG, the short-range transceiver, and the power management circuitry. The long-range transceiver is going to be connected to the PCB through an RS-232 cable. That's this one right here. For short-range communication, that is communication between the local nodes, we have the XB Pro. And now this chip communicates through radio frequencies at 2.4 gigahertz. It's a low power chip that can be mounted on a PCB, its size, and it has a rated coverage of 300 feet. For long-range communication, that's communication beyond the bounds of this XP, we use the Extend, that's this device right here, and this has a rated coverage of 3,000 feet. It uses radio frequency to transmit its messages, and it runs on a 900 megahertz. The slide's meant to give you a visual comparison of the XP and the Extend transceivers. Now these two devices use two different message protocols to communicate, and so they required an intermediate to facilitate the communication between them. This intermediate we chose was the Texas Instruments microchip, which was from the MSP 430 family, that is a family of ultra-low power chips. This particular chip had 3 UART ports, which is basically ports where the microcontroller can talk with other peripheral chips, modules on the board. The board was supported by this power management circuitry that converted the 9 volts from this wall mount to a 3-volt supply that was required by these individual chips. So now talking about how we actually came about designing this board. We used PCB 123, which is a free software by a PCB manufacturing company called Sunstone Circuits. And the first stage of designing this board was to determine the circuitry, the schematic layout, and we used the data sheets of these individual modules to do that. The previous slide was actually the schematic of the microcontroller of this board. The next stage was to put it all together and determine the PCB layout. That's how the different modules are going to be printed on this board. And I thought this was particularly more exciting than the previous one because this is where you actually think about the real things, like the mechanical aspects of it, where do you want the larger components to be placed with regard to smaller components, because this is where issues such as soldering, accessibility might come in. So we had to think about these different implications of our layout. Finally, we sent the design to Sunstone Circuits company, and we had our boards manufactured. These were our boards. I can pass them around for people who are interested. Finally, we had our boards hand soldered with the components on it, and that was our final product. Now Dan's going to take over for the software.
Okay, so to develop the software in the system, we actually use a program called Code Composer Studio. It's a piece of software which you can download on Texas Instruments' website to get a free limited version, but we also had a licensed version in the RFID lab that we were able to use. And we use the software to both write our code, to test our code, and to flash it onto the MSP430 that we used during this project. Now, to talk about kind of the layout and structure of the code that we wrote, there are really kind of two major components to look at. The first one is what we call real-time loop. After we would turn on the machine, initialize all of the pins on the microcontroller, kind of validate that all the peripherals are on and communicating. We then go into a loop where we wait for an event to occur. And we enter into a sleep mode, waiting to get data transfer between one of the peripheral transceivers or also between our RS-232 connector to potentially a computer. We wait in this state until an interrupt occurs in an interrupt service routine, each of these signifying the three peripherals in actual timer interrupt. When we get like a receive message from, let's say, the low power XB transceiver, a flag gets raised which enters us out of our sleep mode into the beginning of our real-time loop, and we check to see which event occurred. It happens to be the receive event, which we would clear our flag, and then actually call the function which receives the message and stores it into our message buffer. And that kind of, so the parts of the components you couldn't see in that flow that were really critical was, first of all, the message buffer. Currently, we can store about 100 messages within the RAM. It can be expanded, but for our purposes, it was just a proof of concept. This buffer is used to store messages that are received within our router, and then that's the location in which we'll find them and transmit them out between whatever peripheral device that we intend to. We have a routing table within the code that checks to see if the device that we're communicating to is within the communication kind of zone for our router. We have two separate tables. These are tables of addresses of the devices that are attached to the network. If the message is to be sent to a device, I want to know if, as a router, if my device was in range. If it's not in the range of the low power transceiver, I might want to check the higher power transceiver, which would actually have a list of the other routers' addresses that it knows, devices that it's connected to. We also have a timer, so we can timestamp logging information and figure out when the messages in some period of time occurred. And we also have software that actually blinks LEDs, so we can get outside indication that we're receiving, transmitting, or if it's in a normal state of operation. Now, to actually send messages, we actually have to create a message format. We actually developed our own format. It's very simple and very basic. First, we have the actual address of who we're sending this message to. And it's a 16-bit address that allows us to have about 65,000 unique addresses. And we also have 2 bytes for sender ID. And the next part, we actually have a possibility to configure variable data length. Right now we work with fixed 8 bytes, but you could potentially expand it up to about 16 bytes of raw data. And we have a thing I like to call a special function check. It's just a place where we can actually indicate some kind of special features of the message. An example, if we got a message and I want to send back to whoever get me the message as a device, that I acknowledge it, I can indicate it there, and I'll send the exact message they sent back to me, just so that they know that it got received. We could even clarify what kind of data we're looking at. An example could be an integer or various other data type. Also, if we're doing a ping, it's just a really quick way to check to see if, oh, this is a device that's pinging me, so got the ping. We also support a cyclic redundancy check, which is a methodology of checking to see if all of the data wasn't corrupted during the transmission. And so this is a network in our current state. We have 2 relay boards that were constructed and tested. All the hardware seems to work with them pretty well. And we also have 2 remote nodes that were completed during a kind of second project by Jellica for an independent study that we also use incorporated into our project. And these are the remote devices. They act as the remote network. Currently, the way that we test these things, we would send a message from a remote device to the relay, which is our router. It acts as a relay to pass through the higher, the longer ranged extend transceivers across the long distance to another relay to potentially another device, vice versa. And we actually tested these things in part here ourselves. We did a couple range testing. The first one we did is we wanted to see how far these small transceivers actually communicated. So we actually stuck them in the RFID lab way at the end of the building in the bottom there, and saw how far we could go and still retain a reasonable connection between the 2 devices. They themselves handle the connection between themselves, so it's easy to tell if we lose connection or not. We cannot upgrade. We were able to get about 245 feet from the 300 feet that they ranged, and I figured because we got concrete walls and a lot of things in between these 2 places, we literally just walked down the hallway for that. We also tested the extend long range, put one in the RFID lab, connected to the computer, and sent the messages across, and we're able to get ranges all the way about to Dean's office up in the C range there, the blue line. Got about 565 feet going through a bunch of different laboratories and walls and through the hallway. And then when we actually combined together having a device in the RFID lab, an actual connection with our routers, here and here, an actual another device, we were able to get a connection from the RFID lab reasonably all the way down to the E section of the building, which was pretty cool. And Jumana talk about the summary.
Here's a table that shows the summary of how we met the specifications and what we used to meet the specifications. We were able to achieve a range of greater than 600 feet by using the extend. By using RF communication, we use the XP Pro S1 and the extend to establish communication in burst noise environments. By using the inbuilt features and modules, we were able to achieve error checking and data transmissions, and we use the extend and the XP Pro S1 for that. As for the physical specifications, for system longevity, we use low power modules such as the MSP430 microcontroller and the XP Pro S1. We were able to achieve a compact system which weighs less than 1 pound by using a PCB and small size modules.
As for applications, now since we're using radio frequencies, this product would be very applicable in environments where noise may be an issue, such as an industrial environment. This project could be used for sending short messages in situations of monitoring inventory and machine diagnostics.
And as for our future developments, we foresee other groups perhaps further developing these devices. The first one being actually simplifying the PCB board, shrinking its area. We figure we can get about 50 to 75% reduction in size now that we've actually validated that our design is functional. We could go about actually upgrading and improving the software that we use in the routers. There's a lot of room with the MSP430, a lot more features you can include to decrease the complexity of the network and allow us to